Okay, let's start.
What I have for today is a method called pulse modulation. The idea here, it was at the beginning point, is to use a sequence of pulses as a carrier. So here in yellow I have sequence of pulse. Can I use the sequence of pulse as a carrier to transfer some information? In general, I can use what? I can use pulse amplitude to encode something. I can use phase shift. It will be analog to angle modulation. Or I can change pulse frequency. It will be analog to frequency modulation. Very popular technique in car industry. Or I can use duty cycle to put some info inside. But first, let's, before analyzing pulse sequence with information, it's good to analyze spectral characteristic of sequence itself. What is spectral characteristics of carrier? Because before we spoke on harmonic carrier, there is nothing to talk about. It has only one spectrum line. Its spectrum is a delta function at a carrier frequency. But here we have something more complex. So we need to understand spectrum of carrier itself. Okay, let's say I have sequence of pulse. Tau 1, tau 2 is timing of pulse, magnitude, let's say E volts, and they are repeating with a period of T0. This point is tau 1 plus T0, and this point will be tau 2 plus T0. So I have the sequence of pulse. What will be mass description for my sequence? It's equals to voltage starting from tau 1 plus m T0 time ending to tau 2 plus m T0. Here m is an integer. Will be minus infinity, blah, blah, minus 1, 0, 1, blah, blah, infinity. And I should write 0 here. Tau 2 plus m T0 time tau 1 plus m plus 1 T0. Here is mass description for my sequence. Okay, I need to decompose it into Fourier law to understand spectrum of the carrier. And here I will see small problem. If I use classical sine cosine orthogonal system, it will lead me to it will be too complex. Much easier is to use system of function sine kx divided by kx. Such system of function works better. So, if I have any periodic function I can substitute my function with a Fourier row. In general, I can use, this is classic, so here classical Fourier row with infinite harmonic components at frequency k double p divided by period. And for each harmonic complex amplitude can be obtained as minus t by half a power minus yacht double p divided by time in time. This is classics. What's not but for pulse sequence, exactly for pulse sequence, I can use this form, tau divided by t0 sine k double p divided by double t0 tau and divided by k double p double t0 tau. I'm deliberately keeping this two. This is trick we saw when spoke on this discrete spectrum. I can represent my signal with its spectrum. So at a frequency space, my voltage can be written as a function of complex frequency. It will be double p divided by t0 spectrum function of my signal. This is Fourier transform of my signal. We know it. We can write double P sum from minus infinity to infinity delta function omega minus k double P divided by T0. Discrete spectrum. We saw it. Sequence of pulse has discrete spectrum. I used exponential pulse. Here, in general, it will be the same. We see infinite number of delta function or infinity thin spectral lines at set of frequency E double P divided by 0. Here, or a sequence of pulse and its spectrum thin lines, but these lines are not equal, not uniform. Since I can represent my signal as a sequence of delta function, minus infinity to infinity delta function P minus empty capital, we can substitute our signal with the infinite set of measurements or delta functions. Fourier coefficients of factor for the signal will be 1 divided by minus t by half, yeah, f power double P. If we perform calculus, what we will get? 1 divided by period. Meaning what in frequency space, our signal can be written as again through its spectral function, and it will be double P divided by repetition period sum from minus infinity to infinity delta function at frequencies omega minus k double P divided by repetition period. We will see sequence of spectral line against with a step double P divided by signal period. Period of our signal is T0, and our signal has a magnitude of E. So it will be double P divided by repetition T0, sum from minus infinity to infinity, sine of K double P divided by double T0, tau divided by K P T0 tau multiplied by delta function at point K double P divided by T0. Set of thin spectrum lines. So for set of pulse, spectrum looks like double P divided by T0. Okay, for P divided by T0, 6P divided by 0, 8P divided by 0, 0 minus double P minus 4P 0 minus 6P 0. Yeah, here is my 1 second. At a 0 point, this point is double P divided by A0, magnitude of A0, it's a magnitude. And I need to draw one line. What's this? At some point, sine of K P divided by time equals to 0. This gives me 0 points. 0 point, this is first, is when m is integer divided by double P divided by tau. See that what's trick here? This is point double P divided by tau, 0 point minus double P divided by tau. Double P magnitude of first harmonic. Again here double P magnitude of first harmonic. This point double P magnitude of second. This point double P magnitude of second. the step of spectral line, distribution of spectral line, is set by repetition period. But zeros, this point, are set by tau. Here's picture. For my case, I have pulse from tau 1 to tau 2, not from 0. In such case, I will see bit more complex picture. So I can substitute my signal width E. This is tau divided by T0 multiplied by 1 plus double sum k to minus infinity to infinity sine of k p divided by T0 tau 2 minus tau 1 divided by kp divided by T0 tau 2 minus tau 1, and this this is first part, multiplication. 1 second, I will write the second one. This formula looks like simple harmonic motion cut out of I don't know pulse. No, it's not so simple harmonic motion. It's more complex. When you deal with pulse, it's more complex. Look at the red line. 1 second, I will write a formula for it. It's not so simple. I have one sequence with one frequency, but look at spectrum. It's a long set of spectral line of delta functions. 1 second, I will continue my formula. K double P divided by T0 minus tau 2 plus tau 1 divided by half. 1, 2, 3. Here is formula when I account for offset. Offset yields cosines, but main spectrum looks like sine x divided by x. Equation I wrote, you may find it in bit different way. Some scholars prefer write it in this way, so I can substitute my as E multiplied by it's tau 2 minus tau 1 divided by T0 plus 1 divided by Kp sum where k is from 1 to infinity sine k omega 0 multiplied by tau 1 minus sine of k omega 0 t minus tau 2. Here omega 0 is double p divided by 0, but again, general idea is to represent signal as a difference of sine. Sine minus sine. Okay, spectrum of carrier. Right. One more. Spectrum of carrier. I can substitute my carrier as E tau 2 minus tau 1 divided by T0 multiplied by 1 plus double sum started from 1 to infinity, sum of what? Of sine k omega 0 tau 2 minus tau 1 divided by half and divided by k omega 0 tau 2 minus tau 1 divided by half multiplied by cosine of k omega 0 time minus tau 2 plus tau 1 divided, this should be divided by half. Here is a situation for spectrum of my carrier for simple sequence of pulses. Since my scope can display only positive frequencies, one moment, I'll try to draw what do we see. Zero, omega 0, double omega 0, triple omega 0, quadruple omega 0, 5 omega 0, 6 omega 0, 7 omega 0, and so on. At some point, cosine of k omega 0 minus tau 2 plus tau 1 by half equals to 0. And at this point, we will, at this mean one, we have 0 point at double p m tau 2 minus tau 1. I don't know, maybe somewhere here. Whoop. 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 That's what we will see in theory. Multiple line, how to say, kept by cosine. Maybe I will increase. This point is double m, double p divided by tau. One moment, I'll enlarge screen of my scope. Here, take a look. Yellow line is a sequence of pulses, and a red line is a result of discrete Fourier transform on it. What happens if I change frequency of pulse? Make myself closer to my generator. Now frequency is at 10 kilohertz. I'm increasing frequency. You see what happens? I'm changing T0. The lower frequency, the higher T0, the more dense is spectrum. The lower T0, we have increase in distance between spectrum line. Now, I will switch to different point. Now I will change tau. I will change duty factor of my pulses. For example, 3, 0. Now it's a 30%. You see, distance between spectrum line remains the same, but caps are changing. For example, 58%. Duty factor, maybe we can go back. 7, 56, 53. Oh, here, 50%. Nice exponential decay. Something, maybe, wait 1 second, 10%. Where is enter? Here, 10%. And you see, here is spectrum at 10%. See these waves. To comparison, 3, 0, 30% duty cycle, or 60% duty cycle. 3, 0. 30% duty cycle. Okay. 15%. Very nicely visible. So, change change of period or frequency of sequence changes distance between spectral line. Duty cycle or change of tau changes these waves, changes the 0 points. Oh, nice. Set of waves. This is carrier itself. Can we try to put a signal inside? For example, like this. Oh, I'm using 1 kilohertz sinusoidal signal to modulate magnitude of my pulses. Just to make it visible. Oh, you can see magnitude of pulse changes in accordance with harmonic signal. Here they are. Magnitude of pulses changes with harmonic signal. This is called impulse amplitude modulation, or AI. So it's easy. Easy form when impulse, pulse amplitude is subject sine omega s t. M modulation depth, omega s, in my case 1 kilohertz, from test signal generator. Zero. 0. This is tau 1, tau 2. Here will be 2. Plus. And next one, and next one. One pulse, second, third, one more, so on. Sequence of pulse modulated with harmonic signal. I can write my signal. This kind of signal of image sensors. They can refine such kind of signal. So it will be E1 plus M sine omega st. In case minus t by half plus m t0 time tau by half plus m t0 and 0 and tau by half plus m t0 time minus tau by half plus m plus 1 t0. We can use known spectrum for carrier and linearity of Fourier transform and write our voltage S E1 plus M sine omega st tau divided by t0 multiplied by 1 plus 2 sum from 1 to infinity sine omega 0 tau by half divided by omega 0 by half tau multiplied by cosine of omega 0 t. Now it's time to take trigonometry book and simplify this. After trigonometry, small trigonometry block, I can write my signal in the way E tau divided by t0 1 plus m sine switch omega st plus double sum 1 to infinity sine k omega 0 tau by half divided by k omega 0 tau by half multiplied with cosine of omega 0 times plus will contain one moment, will contain tiny formula plus can I erase? Yeah. Plus modulation depth divided by half sine omega 0 plus omega s time minus omega 0 minus omega s time tiny formula. It's tiny formula. What this mean? First I'll draw it in theory, and then we will try to see is this true. We should see something like this. 0, omega 0, double omega 0, triple omega 0, quadruple omega 0, 5 omega 0. Or somewhere here is a point. This point is double p, 1 double p divided by tau. And somewhere here should be 2 double p divided by tau. 0 points. Whoop, whoop, whoop. Inside. Now, these blue are spectral lines of carrier sequence. And near them omega 0 minus omega s, omega 0 plus omega s. This one double omega 0 plus omega s. Double omega 0 minus omega s. And so on and so on. Here, for example, quadruple omega 0 minus omega s. Quadruple omega 0 plus omega s. In theory, we should see spectral lines of modulating signal are modulating with pure sine, which has only one spectral line. Around each line of the carrier sequence spectrum. Power sequence itself is represented with blue lines. Orange lines are spectral lines, spectrum of my signal, my inflow. Let's take a look closer. 1 second, here it how to say from the distance, and we see appears spectrum lines of the carrier. But if we change scale, who it is? Look who's near. 1 second, I will bring my cursor here. Central line, one of them, 10 kilohertz, and near 11, 9. See what happens? I have sequence of 10 kilohertz, pulse with frequency of 10 kilohertz, modulated with 1 kilohertz. And what I see, around each line, 10 kilohertz, 20 kilohertz, 30 kilohertz, 40 and so on, I see this smaller. These are spectral lines of my modulating signal. If, take a look, I'm adding, one moment, come here. Here, blue line is signal I'm using to modulate. Schooling and why? Yes. Here. Sure. Okay, where we are? One second. I will add, let's make our signal familiar. I'm adding third harmonic to my signal. And maybe fifth. Sorry. This way. Oh! Bit out of synchronicity. So try to. Maybe 1 moment. Oh! My signal contains 1 omega, three and 5. And who's that? 1, 3 and small 5. Maybe switch to logarithmic mode. Here, in logarithmic scale, they may be better visible. See? Third and fifth. First harmonic, here. First harmonic, third, fifth. So what we see? We see spectrum of this modulating signal. I'm transferring this with pulse sequence, using it to key as key to amplitude. And I got its spectrum around each line of carrier spectrum. In general scale, K is spectral lines of carrier, and in detailed view, around each spectral line of carrier, I see spectrum of my carrier signal. Not a very profitable thing. Once it was believed, because pulses can be average power for pulse sequence can be the same, but pulse itself can be like discharge of some kind of energy storage. It was believed that this signal can be used for long-range communication, but no. The only place where it lives, it's readout from arrays of optical sensors. Now it's somewhere deep inside EC circuit. One more moment. If we have sample and hold systems, we may deal. It's not a very common thing. Now, in present day, it was say large schematic. Now it's inside some AC integral circuit, but just for understanding. For example, as one of the way pulse modulation may work, it's model when signal value is kept at a beginning of the measurement. So, set 0. Model like this. It's a signal. It's after sample and hold. This is not. It's inside an analog to digital converter. Why we are maybe interested in spectrum? Because of interference. In early days, sample and hold devices were separate, so the signal was available to test. Now it's somewhere inside, but it exists. Just for knowledge, spectrum of such signal, I can substitute it with the following row. And tau divided by T0. 1 plus m sine omega s tau by half divided by omega s tau by half. I'm taking the simplest possible one single tone signal at input of sample hold unit multiplied by sine omega s plus double A. Who's writing sum like this? From 1 to infinity. Maybe I need to switch cameras. Sine omega 0 tau divided by half divided by omega 0 tau by half multiplied by cosine of n omega like n 0 time, it should be n. Plus, to be continued, I will continue on next day. What a spectrum. Can I continue? Yes. So cosine plus modulation depth by half sine k omega 0 plus omega s by half, and that's not all. Wait 1 second. Here should be tau or divided by k omega 0 plus omega s tau by half multiplied by sine of k omega 0 plus omega s multiplied by time minus to be continued. Yeah, it's for sine. It k omega 0 plus omega s in parentheses multiplied by time. And one more. And one more. Why I wrote this? Minus sine k omega 0 omega s tau divided by half divided k omega 0 plus omega s divided by half. Or multiplied with the sine of k omega 0 minus omega s time I can try to draw spectrum of this. Frequency. Omega 0, double omega 0, triple omega 0, quadruple omega 0, 5 times omega 0. Somewhere here. Distance between this is m by half. And we will get here at omega 0 goes up. This signal appears to be asymmetric in its sideband. This point, omega 0 plus omega s. This one, omega 0 minus omega s. Double omega 0 minus omega s. Double omega 0 plus minus omega s. It's signal with asymmetric bands. Okay. Maybe we are limited in time. In case we use, it's very common for automotive industry, use voltage, airflow, temperature, voltage as a frequency of pulses. Just for understanding, this type of signals are not for long range. And then, let's say, I can write results. If we have single tone modulation, so for when signal is encoded as a frequency of pulse, so T0 is a function of S naught K. No, in our case, linear. Signal can be substituted as A tau divided by T0 minus double modulation D divided by T0 sine omega S tau by half multiplied by cosine of double P divided by T0 10 minus tau by half plus I will continue on next table because it's a big object. Can I erase? Plus sum, starts from 1 to infinity, sum where m starts from minus infinity to infinity, double divided by kp, Bessel function of order m at k m double p divided by 0 sine of goes here k double p divided by T0 plus m omega s divided by half multiplied by cosine k double p T0 plus m omega s maybe I continue here. Time minus m omega s tau by half. So it will depict spectrum of frequency modulated signal around each spectral line of carrier. Now, which of modulation is most popular? Both nowadays, both pulse amplitude and pulse frequency, a bit more popular. Pulse amplitude is hidden somewhere, but what is very popular? PWM, pulse width modulation. pulse width modulation. In pulse width modulation, tau is a function of signal how to be transferred. But in reality, it isn't used for data or sound or info transfer. PWM technology extremely popular now to control energy. All kinds of electronics need stable DC voltage. So conversion from nets AC into electronics DC is done today mostly with PWM idea. How it works? Take a network voltage, this 230 volt, rectify into DC, it will be 300 volts, then switch controlled by PWM. You may need some snubber here, but it's not important. Important secondary side, your load, and this is feedback for, let's say, maybe 100 kilohertz, maybe 200, something like this. Switch is on, off, on, off, on, off. Simple idea of impulse with modulator. Take voltage like this and compare it with UFB. Q is switch. If, for example, voltage decreases, I don't know, because increase of load. Voltage decrease. Width of pulse will increase and transformer will get more energy. If another case, I don't know, wait, oh, yellow. This case, voltage increases, amount of energy transformer received will decrease, and voltage will go down. One moment, I'll free some space on my table, and I'll get device of this kind. in the example. It's a power supply from cash register. Yeah, it's small. Yeah. Transformer. Switching transistor. Let's try to see inside, but please, here, large disclaimer. Do not try this at home without training and precaution, because it's dangerous. It is not safe to dig inside such power supply. One moment, you'll see. What's inside? It is dangerous. Do not try to operate without precaution. Insulating transformer and high precaution is needed. Or you can be electrocuted. Say ah. Here it is. This is transformer's voltage relative to positive path. It appears inverted. Never mind. Take arm changing load. Load decrease. Here, these two bulbs are my load. Load increases. Load decreases. Load increase. Decrease, increase. You can see change in pulse duration. This is action of PWM. Load changes, duration of pulse change. I can simulate this with change of primary voltage. Primary voltage 120 volts. I'm increasing voltage to 130. Voltage decreases, voltage increases. Voltage decrease, voltage increase. PWM keeps area of this pulse and amount of energy transformer gets constant. You see? Area of pulse remains constant. Spectrum is complex. You see, it's a spectrum of carrier we saw before. One moment. First, I'll try to. With a bit of help, here, spectrum of the voltage. Uh, 100 kilohertz. Don't look at this big. It's not 35 volts. It's 300. It's 350 volts. This, yeah, it's 350. It should be multiplied by 10. If you get such discharge through your head, it will or kill you, or because blood circulation will be disturbed, you can remain brain dead. You will become vegetable. So please, without extensive training, do not try to put your finger inside a PWM operated power supply. Small mobile charger can kill you. It's strange, but small are more dangerous. Discharge of such powers through head will disturb its operation. It can suppress your brain center. So do not try this at home. Special care is needed. Here. Spectrum. Okay, so rewind back to the beginning of lecture. Actually, it's a spectrum of what I started with the carrier, but in case of PWM, tau changes. Tau is a function. This is T0, it remains constant, but tau, let's see, tau changes. Oh, this one near resonant, it's also this design of power supply allows free oscillations of transformer primary winding. In different designs, there is no this free oscillating part. I can try one moment. Come here. Here around spectral line is nothing. Only carrier. This part, free oscillations. Extremely popular technique nowadays, just because it's small. Such power supplies are small in geometry, in weight. PWM impulse width modulation is most desired kind. Okay. Yeah.